All right, guys, hello. This is my promise to you that I was going to make up for that lost time yesterday during the fire drill by doing some problems from the review session number 2 handout that is in Canvas. During the first review session, we got several of the problems done already. And then during class, I actually used some of the other problems from this review session sheet as my examples that we looked at. So we've already seen a fair number of these. And don't forget that I have typed up the solutions already, and those are in Canvas. So if you want to take a look at that as well, you certainly can. But I'm going to do these particular problems from that review session handout during this video. So it'll take a little bit of time, but there'll be a lot of good stuff to review along the way. I'm not necessarily going to go in order. I'm going to go kind of, in whatever sequence sort of makes the most sense to me. I'm going to definitely do these examples involving field extensions since we didn't do a lot of that during the first review session. So I'm going to start with problem number 2 off of the handout. And let me write it down really quickly. We're going to take the field F to be the rational numbers. And K is going to be the extension where we adjoin the square root of 2, the 5th root of 5, and the 7th root of 7. And there's 2 parts to the question. The first part is just asking us to compute the dimension of K over F. So they want us to compute this dimension. And in order to do that, what we might think about is not thinking directly from F to K, but recognizing that there are several intermediate fields here that we can take advantage of. So I'm going to draw a little tower. It's always a nice idea to understand the relationships between these fields. But one way that we could make a tower would be to just directly adjoin one element at a time until we get all the way up to K. So I could build a tower like so, where I have the rational numbers on the bottom, and then I can do a simple extension where I adjoin the square root of 2, and then another simple extension where I now adjoin the 5th root of 5, and then another simple extension where I adjoin the 7th root of 7 in order to get K. And the question that I'm trying to figure out here is, what is this dimension? What is the dimension of K over F? In this case. All right. So the tower theorem tells us, so we know from the tower theorem, and it's okay to just cite that. You don't have to have the number from the book. You can just cite the tower theorem. That dimension of K over F is the products of all of the smaller dimensions going from each field to the next one up. So I can view this as the dimension of K over Q of square root of 2 and 5th root of 2. And then I can multiply that by the dimension of Q of the square root of 2 and the 5th root of 2 over Q of the square root of 2. And then I can multiply that by the dimension of Q of the square root of 2 over Q. So the tower theorem would tell me that the dimension of K over F is the product of these 3 numbers. Okay, so we have to now imagine, well, what would be each of these dimensions along the way? We do know that the dimension of a simple extension over a base field is always equal to the degree of the irreducible polynomial of the element that has been adjoined over the base field. So for example, this one is really easy because the irreducible polynomial for the square root of 2 over Q, and we can write it this way, as you know, would just be x squared minus 2. I'll remind you that this is irreducible by Eisenstein's criterion applied to the prime p equals 2, or it's irreducible because it has no roots in Q. The roots of this polynomial are obviously plus and minus the square root of 2, which are not rational. And so therefore there's no roots in Q. And if we don't like that reason, we can give a second reason, which is just applying Eisenstein to the prime p equals 2. So because this adjoined element has a quadratic irreducible polynomial, I know that this dimension is 2. No problem, right? What about this one right here? Now here's where it gets a little tricky, because the element that I have adjoined is the 5th root of 5, right? I have my base field here, and then now the extension, the new element that I have adjoined is the 5th root of 5. Now we can look at that and we can say that the 5th root of 5 satisfies, there is obviously a polynomial that it satisfies, which is x to the 5th minus 5 equals 0. Okay, now that might be the irreducible polynomial for the 5th root of 5. The issue is, although this is clearly irreducible over Q, it's irreducible over Q again by using Eisenstein's criterion with the prime p equals 5. However, Q is no longer the base field anymore. The base field is now a much larger field that we cannot apply Eisenstein's criterion to. And the degree of the polynomial is now big enough that we can't just wonder about what the roots are. I mean, in other words, even if you can convince me that there's no roots in this field, I still don't know that I might not be able to factor it as, say, a quadratic times a cubic or something like that. So this is all of a sudden become much more difficult. However, what we can say is that this dimension is at most 5. It is at most 5. Now, why is that? Well, that's because if this isn't the irreducible polynomial for the 5th root of 5 over q adjoined square root of 2, then the irreducible polynomial for the 5th root of 5 could only be a smaller polynomial than this one, right? In other words, if it was possible to factor this, then you're factoring it into two polynomials of lower degree, which means that this dimension of this simple extension could only go down. It could only go down. So this is at most 5. Okay. Now I'm going to let you use the same reasoning on the upper extension here. I've adjoined the 7th root of 7 to q adjoined square root of 2 5th root of 5. And again, the 7th root of 7 satisfies x to the 7th minus 7 equals 0. So once again, it's not clear that that's the irreducible polynomial for the 7th root of 7 over this field. Right? If it was over q, we'd be in great shape, but we don't know that. So all we can say here is that this is at most 7. It might factor. It might factor if I'm allowed to use this large base field as my scalars. This could factor into a cubic times a quartic, for example. And I don't want to try to think about whether that's true or not. But what I can say, based on everything here, my friends, is that this is at most 70. It's at most 7. And I'm actually going to convince you that it's actually equal to 70. By the way, feel free to pause this video. You don't have to just listen to my explanation. If you want to try for yourself to figure this out, that's even better. So we've got that the dimension is at most 70. And what I'm going to do next is actually convince you that it's at least 70. It's actually at least 70. And I'm going to use the tower theorem to do that as well. But I'm going to draw my tower a little bit differently. I'm going to draw my tower a little bit differently to try to convince you that this dimension is at least 70. So it's at most 70, and now it's going to be at least 70, which means the correct answer is going to be 70. Why is it at least 70? Oh, this part is actually easier. This part is actually easier. If I put k at the top and I put q at the bottom, what I can do is I can adjoin the square root of 2 there, or I can adjoin the 5th root of 5 here, or I can adjoin the 7th root of 7 here. And as long as q is my base field, I can use these polynomials in the full knowledge that they are irreducible over q by Eisenstein, right? Here p is 2, here p is 5, here p is 7. So my friends, this is 2, this is 5, and this is 7. Right? There's no doubt about it, right? The degree of each of those simple extensions is just, or sorry, the dimension of each of those simple extensions is just the degree of the irreducible polynomials. And these polynomials that I have circled, they are irreducible over Q. The issue up here with these inequalities was that the base field wasn't Q, right? When the base field is not Q, then irreducibility is a much murkier thing, right? So take a look at what we have here, right? This dimension from K over Q, which is just K over F, right? By the Tower theorem, so say by the Tower, this number is a multiple of what? Multiple of 7. And if I go this way, it's multiple of 5. And if I go this way, multiple of 2. And if you have a number that's a multiple of 7 and a multiple of 5 and a multiple of 2, then since those are relatively prime, we can say that it's a multiple of their product. So in other words, this dimension is a multiple of 70. It's at most 70, but it's a multiple of 70, right? Well, that's not going to leave us very many choices, right? So if this dimension is a multiple of 70, then putting that together with the fact that the dimension was at most 70 allows us to now conclude that the dimension is exactly 70. And it's kind of interesting. You prove what this number is by proving that the dimension is less than or equal to that number and greater than or equal to that number. And it's surprisingly difficult to prove directly that it equals that number. We kind of have to take this roundabout approach. So that is part A of problem number 2. Okay, so hopefully that makes sense. Turns out that these 3 polynomials that we've circled, they are all going to be irreducible over their base fields, right? Because the fact that the inequalities turn out to actually have to be equalities means that you basically do have the irreducible polynomials. So if I asked you to prove that x to the 7th minus 7 was irreducible over Q adjoin square root of 2 fifth root of 2, we now know that because this dimension is equal to 7. And it's not anything less than 7. So, yeah, let's take a look at part B, which is kind of related to this example. It just asks us to prove that this polynomial over here, x cubed minus 2, is irreducible over K. Now, if we were asked to show that it was irreducible over Q, it would be easy because we could just use Eisenstein's criterion with P equals 2. But we're testing for irreducibility over a weird field right now. Okay, let's suppose for a minute, by way of contradiction, that this polynomial was not irreducible over K. So this is going to be a nice proof by contradiction. Proof by way of contradiction. If it wasn't irreducible over K, then what would that tell us? Well, it would mean that it's reducible. And because it's a cubic equation, remember guys, if a polynomial has degree 2 or 3, then it is reducible if and only if it has a root, right? So by way of contradiction, if f of x was reducible, right? Then, but because it has degree 3, since the degree of f of x is equal to 3, could you sit somewhere else? Yeah. If this polynomial is reducible, since it has degree 3, then it would have to have a root. So then f has a root, I'll call it u in K. And what you might notice here is that allows us to build another tower. Oh my gosh, this tower theorem is so incredibly important, right? So what would this tower look like? Well, we could consider the tower. Let's go ahead and draw it. Right, Q would be at the bottom of it, right? And then what I could do is I could say, well, let's do Q adjoin U, right? And then let's go up to K from there. Now, when you're drawing a tower like this, it's always important to make sure that each of the fields is a subset of the field above it in the tower. So obviously Q adjoin U contains Q, but I need to know that K contains Q of U. Well, that's where this is very important, right? The fact that U belongs to K, right, tells me that everything in Q of U belongs in K. Great. So I have this tower. Now we already proved in the first part of the problem that this dimension was 70, right? And so do we see how we can get a contradiction here? Remember this dimension, this is a simple extension. So what's the dimension of it? It's just the degree of the irreducible polynomial for U over Q, right? So what's the irreducible polynomial for U again? Well, it's a polynomial that U satisfies, right, with coefficients in Q. And it's exactly this guy, right? So this, the irreducible polynomial for U over Q is x cubed minus 2, right? Remember, f has a root. So U is a root of this polynomial. U is a root of that polynomial, and that polynomial is irreducible over Q. And so that makes this number equal to 3. That makes this number equal to 3 because it's a cubic polynomial. Okay, and so by the Tower theorem now, 3 divides 70, which is a contradiction. Okay, great. Feel free to pause the video, take it all in, and then we're going to move on to a new problem. Okay, guys, so we have just done number 2. I think I'm going to go on and do problem number 19 next, because this one's really fast, and I like to cross numbers off of my sheet fast as quickly as possible. So on number 19, it says, find a basis for Q of the square root of 2 plus the square root of 3. So we've adjoined the element radical 2 plus radical 3 over Q adjoin radical 2 comma radical 3. So feel free to pause the video, and maybe we've seen this before or seen an example involving these 2 fields before. I don't know if you remember, but we actually have proven already that if we adjoin the elements one at a time, right, each of these extensions has a dimension of 2. So this full dimension is 4. But on the other hand, if you look at Q of radical 2 plus radical 3, that's actually, well, I'm going to draw it over here on the side. That's actually contained in there, because square root of 2 plus square root of 3 is part of this field. But we also, we computed that there was an irreducible polynomial of degree 4 for Q of radical 2 plus radical 3. Which, I don't know if you remember that, but basically what that says is that this dimension has to match this dimension. And so therefore, what does this value equal? It's actually equal to 1. And so we used this Tower theorem to prove that these 2 fields are actually equal. Remember, if the dimension of an extension is 1, it just means that the 2 fields are the same. Okay, so note, this is from earlier. We did this in class, actually. So that these are actually equal. Q of radical 2 plus radical 3 is actually equal to Q adjoin radical 2 and radical 3. And I could just say see lecture notes here. If you want to review that, or you can just try and convince yourself. It's basically this. It's basically this tower here. You have to actually find the irreducible polynomial for radical 2 plus radical 3. But once you've done that, everything is good to go. Awesome. So if these 2 are equal, then tell me what would be a basis for this field over this field. What's always going to be a basis for F over F? Pause the video if you want to. Think about it. You know that it's a dimension of 1. So when I'm asking you for a basis here, I'm only asking you to give me one single vector. And what we're saying now is not just for this example, but for any time you're asking for the dimension of a field over itself, right? You can just choose a basis of 1. That's it, because everything in, right, everything in this field can be written as something from here times 1, right? Because the fields are equal. So this is kind of trivial. It's just a triviality. Anytime the dimension of the field extension is 1, well, then you can take a basis of just 1. That's number 19. I told you I wanted to get it done quickly. Okay, awesome. Let's do another example. Let's do number 20. We're on a roll with the field theory, so I think I'm going to keep going with it. Let's compute the dimension of Q adjoin radical 2, comma, radical 5, comma, radical 10 over Q. So in this case, again, we're going to try to use the Tower theorem, I think. Notice that adjoining the square root of 10 isn't really necessary here, because I can already make the square root of 10 by just multiplying radical 2 and radical 5. I can kind of just ignore radical 10 here. And I'm really just looking at this extension here. And again, I would like to know what the dimension of it is. And I have a nice intermediate field here that I can use, which would be, let's just say Q adjoin the square root of 2. So we can just build this little tower. And I know that the element that I adjoined here, which is the square root of 2, has an irreducible polynomial over Q of x squared minus 2. And we talked earlier about why that's irreducible over Q. There's multiple reasons we can give. But because that's a quadratic, then I know that this dimension here is 2. And then it's just a question of, well, what is this dimension up here? And again, I know that the square root of 5 satisfies x squared minus 5 equals 0. So at worst, this irreducible polynomial is degree 2, which would mean that this is a 2-dimensional extension. Turns out it actually is 2. How do you know that you cannot? How do you know that this is irreducible over this field? Well, the fact of the matter is I know how to factor it. I know how to factor it. It would be x minus radical 5 times x plus radical 5. The question is that factorization legal if this is my field that I'm allowed to work with? And the only way it would be legal is if the square root of 5 lived in here, right? So the question we could ask ourselves here is the square root of 5 an element of Q adjoin the square root of 2? Pretty clear the answer will be no, but I'm going to just show you why, because I don't like to leave any stones unturned here, right? If we imagine trying to write the square root of 5 as an element of Q adjoining the square root of 2, we would be writing it as such, namely in the form a plus b radical 2, where a and b are rational numbers. And what we can now do, pause the video if you don't want me to spoil your fun. I'm trying not to make things go too long. But what we can do now is just simply square both sides. So if I now square both sides of this, I will get something that looks like the following. Something like the following. And if I solve that for the square root of 2, what I'm going to be proving here, which is going to be my contradiction, this is going to be a contradiction, guys, right? My contradiction now is going to be that if a and b are rational, and I make this fraction here, it's still in Q. This would be proving that the square root of 5 is rational. And that is simply not the case. This is a contradiction. And therefore, this factorization is not legal, which means that this polynomial does not have any roots in Q adjoin radical 2. There's no roots. And since it's a quadratic, it's actually irreducible. So in other words, what we're saying is that this guy here is actually the irreducible polynomial for the square root of 5, even over this somewhat murky field Q adjoin radical 2. Right. So the irreducible polynomial for radical 5 is actually that, and that means that this is a 2. And so then by the Tower theorem, the big dimension is actually equal to 4. The answer is equal to 4. Good enough. Hope that makes sense. If not, come ask me. I'll talk to you about it some more. All right, guys, I'm going to continue with the field extension theory here. Let's do number 17 next. It's actually got 3 parts, but these are all really quick. It says find a basis over Q for each extension. So there's actually a couple of parts here. This goes really quickly, so we'll just do it relatively fast here. So part A, we're going to look at the extension of Q adjoin the square root of 2, comma, the cubed root of 2. So now I'm adjoining 2 elements, first radical 2 and then cubed root of 2. And the way that you want to approach this is to remember the proof of the Tower theorem, because I can draw a tower here. Maybe I'll just do it this way. It doesn't matter which element you adjoin first or second, but I can draw my little tower like usual. And if I can find a basis for each of these simple extensions independently, then the Tower theorem proof showed us that to get the basis for the large field over the base field, we need to just multiply the basis vectors from here with the basis vectors from here. So we just want to find these individual bases. That's basically what I'm going to try to do here. So what is a basis for Q adjoin the cubed root of 2 over Q? Just to remind you, with a simple extension, this comes from the simple extension theorem. One of the parts of the simple extension theorem is that the basis for this larger field, extension field, as a vector space over the base field Q is simply obtained by taking powers of the element that you have adjoined. So 1 cubed root of 2 and cubed root of 4. I don't need to go any further than that, because the next one I would write down would be the cubed root of 8. But the cubed root of 8, of course, is just 2, which means I'm creating a linear dependency with the first vector. So we would just write down those 3 powers. Remember, we know this is 3-dimensional. Right, we know this is 3-dimensional because the irreducible polynomial of the cubed root of 2 over Q would have been this guy. So if it's 3-dimensional, then I better be writing down 3 basis vectors. Okay, basic linear algebra 101 tells us that the number of vectors in a basis should match the dimension of that vector space. Okay, beautiful. So I've got that basis. Now what about the one up here? The one up here at the top, I have adjoined the square root of 2 to this basis. And so this is going to be just 1 and the square root of 2. Already, I cannot go any higher than that. If I take the square root of 2 and I square it, well, then I'm back to a multiple of 1 again. So this is going to be the whole thing. The only question you might ask me right now, that you might play devil's advocate, would be, is it possible that these 2 fields are actually equal? Ask yourself, is it possible that they're equal? But the answer turns out to be no. If you really wanted to explain why not, so this is a 3 here. If I did come over and just adjoin the square root of 2, this would be a 2. So kind of using the reasoning from the very first example I did in this video, this dimension has to be at least 6, because it has to be a multiple of 2 and it has to be a multiple of 3. So therefore it has to be at least 6, because the smallest thing that's a multiple of both 2 and 3 would be 6. So if this is at least 6, and this one's only 3, then this has to be at least 2. So it's at least 2, it's also at most 2, therefore it equals 2, and here's my basis. Okay, so then how do I get my basis for the final answer here? The basis for the basis over Q for Q adjoin the square root of 2 and the cube root of 2. Okay, so remember how we do that? We just multiply, we mix and match products of something from here and something from here. So 1 times 1, 1 times radical 2, cube root of 2 times 1, cube root of 2 times square root of 2, cube root of 4, and cube root of 4 times square root of 2. Those would be all of the options. And there should be 6 vectors there. And that's consistent with the fact that we would expect this to be a 6-dimensional extension. So again, if I have a tower situation and I have bases for each layer of the tower, then to get the basis for the large top of the tower over the base field at the bottom of the tower, I simply multiply each basis vector from here with each basis vector from here and write down the list. Okay, you don't have to prove that this is a basis because that's coming from the tower theorem, right? The tower theorem basically proved that, yeah, if you have this basis and you multiply them, you still have a basis again. So it's perfectly okay to view it that way. Okay, let's try another example. Again, feel free to pause if you need to reflect on this or spend a little more time with it. Okay, guys, I'm just going to try another one with you now. Again, I'd like to write a basis for Q adjoin square root of 5 and I over Q. Works the same way. Works the same way as before. So what we can do is we could imagine building a tower. Again, I kind of like to do the square root of 5 first, because it's very clear that this dimension here is going to be 2 with a basis of 1 and I. While the dimension down here is obviously also 2 with a basis of 1 and the square root of 5. So I'll leave those calculations to you, and then to get my final basis here, again, feel free to pause the video if you want to write it down for yourself first, but it's pretty straightforward. We just take every possible combination of something from here and something from here. So 1 times 1, and then 1 times I, and then radical 5 times 1, and then radical 5 times I. And that would be the basis in that case. Awesome. Okay, let's do one more. And I think we'll be good on this. This next one is a little bit bigger. What if we wanted to do Q adjoin square root of 2, square root of 3, and square root of 5? All 3 of those. So when I say it's a little bit bigger example, what I mean is that the tower is a little bit bigger. So I could imagine adjoining each of these 3 elements one at a time. Right, so in this case, we have, you know, a larger tower than normal, but all of these dimensions are going to be 2. And so as a result of that, we are going to end up with an 8-dimensional vector space. The basis in the first case is 1 and radical 2. The basis in the intermediate case is 1 and cube root of 2. And the basis in the top case is 1 and the square root of 5. Sorry, I meant to say square root of 3 here. I think I said cube root of 2. Sorry. So this basis is 1 and the square root of 3. This basis is 1 and the square root of 5. Awesome. So now I'm going to do a 3-way mix and match, right? Grab one of these, and one of these, and multiply them together to get my large basis. So here I'll have a basis consisting of, so I'll start with 1 times 1 times 1, which is 1. And then I'll do square root of 2 times 1 times 1, which is the square root of 2. And then I'll do 1 times the square root of 3 times 1, which is the square root of 3. And then I'll do square root of 2 times the square root of 3 times 1, which is the square root of 6. And now I have to take all of those and multiply them all by square root of 5. So I'll get square root of 5. The square root of 5 times the square root of 2 is the square root of 10. The square root of 5 times the square root of 3 is the square root of 15. And the square root of 5 times the square root of 6 is the square root of 30. And so you see here, we have an 8-dimensional vector space. Anything in Q adjoin radical 2, radical 3, and radical 5 can be written as a linear combination of those 8 terms. So it can be a little bit messy looking, but that's the idea behind it. If you didn't like doing the 3-way mix and match, you can of course view it in a staggered way. You could say, well, let's just get this basis first, right? Just from here to here. And if you did that, of course, you would just get the first, using the same result, you would just get the first 4 elements in the basis over there. And then I would take that basis together with the top basis to still get those same 8 elements. So if you don't like to think of it as using a three-way simultaneous product of something from here, and something from here, you can always break it down into just 2 steps at a time. Okay, I hope that's clear. We've done 3 examples of it. It works the same every single time. When you're using the Tower theorem to do this, you just multiply the bases from each intermediate extension to get the big full basis for the top field over the bottom field. Okay, guys, we're making our way through the field theory here. I'm going to do one more field theory example right now, which is number 16. And this one is related to the one we just did, so it's good timing to do it. It just says in the field Q adjoin the cube root of 2, express the element 2 minus the cube root of 2 quantity inverse. So we're in a field, so every element that's non-zero has a multiplicative inverse. I would like to express that element as a linear combination of the basis. I actually should write down what basis I want to use. Remember, a basis is not unique. And I notice here in the question, it doesn't give us a basis, but we're going to use this field. So the natural basis to use over Q would be just the powers of that adjoining element. So 1 cube root of 2 and cube root of 4. 4 Q adjoin the cube root of 2 over Q. Okay, so this is what we're going to look at. So we have an element that is in this field, and I would like to express what its inverse is. I mean, everything in the field should be expressible as a linear combination of the basis. A basis is supposed to span the field. So this field is spanned by these 4 guys. That means that this element should be expressible in terms of these 3 guys right here. So I'm going to try to do it. Now, in this case, I don't really know exactly how to do it, but what I'm looking for is I'm going to write the inverse using a reciprocal notation here. What I'm looking for is some way of writing this as a linear combination of the basis that I just wrote down for Q adjoin the cube root of 2 over Q. So it's going to have this form right here. Okay, this is actually a rather computational problem. What I'm going to do is clear the denominator here so that I can get something that won't have fractions in it. So I'm going to write 1 as a 2 minus the cube root of 2 times the quantity A plus B times the cube root of 2 plus C times the cube root of 4. So this is the way I'm going to do this. My goal here is to solve for A, B, and C. And let me point out, of course, Dave, that these are rational scalars because we have a basis over Q. So the scalars are rational numbers here. And what we want to do with this is actually just literally FOIL it out. Okay, and then let's see where we're at when we do that. So I have 2 times a, right? And then I have plus 2b times the cubed root of 2. And then I have plus 2c times the cubed root of 4. And then I have minus the cubed root of 2 times a. And then I have minus the cubed root of 2 times b times the cubed root of 2, which is actually the cubed root of 4 times b. And then the last term is the cubed root of 2 times the cubed root of 4, which is actually the cubed root of 8, which is 2. So this will have a minus 2c on it. Okay, because the cubed root of 2 times the cubed root of 4 is the cubed root of 8, and so I can write that as just 2c. Well, guys, this is actually laid out beautifully for us, because what we can do is combine together some of these terms. So I can take the 2a together with the minus 2c. Let's actually subtract the 1 to the right-hand side as well. So I'm going to put the minus 1 over here on this side. And then, so those are the rational terms of the expansion that we have here. And then what else do we have? Well, we have some terms that involve the cubed root of 2. I have a 2b, and I have a minus a, that's multiplied by the cubed root of 2. And then, let's see, check that one off, and that one. The cubed root of 2 was here and here. And then on this one, we have 2c minus b times the cubed root of 4. Make sure I did all that right. Hopefully the calculations look good. Of course, because these elements are a basis up here, if I have a linear combination of them canceling out to 0, then because they're linearly independent, every single one of these coefficients now actually has to be equal to 0, right? So that's going to be the next conclusion that we're going to make. Okay. And again, we have A, B, and C. We would like to solve for those scalars, and I have basically 3 equations here. Okay, notice that A is equal to 2b and B is equal to 2c. And from that, I can see immediately that A is actually equal to 4c. And so 2a is equal to 8c. I'm going kind of fast, but this is basic stuff here. So I can take the 2a right here and replace it with 8c. And the minute I do that, then I have 8c minus 2c, which is actually 6c minus 1. It has to equal 0. And so I believe I'm doing some of this in my head, and I'm doing it kind of quickly, but you guys can go at any pace you want by pausing my video here. I believe that c should just be 1 over 6. And b is just double that. So b would be 1 over 3. And then a is just double that. So I multiply by 2 again to get a. A would be 2/3. Okay, so my final answer then would be to take this expression that we started with and just put in the values for a and b and c. So I'll put in 2/3 for a. I'll put in 1/3 for b. And I'll put in 1/6 for c. Those are the values. So this is actually a fairly elementary computational type of problem involving the basis for q adjoining the cubed root of 2 over q. Take it all in, pause the video if you need to, and then I'm going to erase and do another problem. Okay, guys, I'm going to go ahead and do number 10 now from the review session problems. And this is similar to several others we've already done today. So if you want to just totally turn me off and just do it before I say a word, feel free to do that, because it is very similar to some of the examples that we have already seen. So we're going to try to show that this polynomial p of x, which is this 5th degree polynomial here, that it has no roots in q adjoining the square root of 2 and the 6th root of 6. So that should be kind of an interesting problem. Now, we did one similar to this earlier today by way of contradiction. So let's imagine kind of doing that approach here again and see if maybe we're a little bit better at it this time. Now that we've seen one example before. So I'm just going to say by way of contradiction, suppose P of X has a root, which I'll call U, which is an element of Q adjoin the square root of 2, comma, the 6th root of 6. So let's just suppose that we had that. Okay, and if you remember from the earlier example, the thing that we can do as soon as we've done that is we can build a tower, right? So we can consider a tower now. How does the tower work? Well, I'm going to put Q at the very bottom of it, and then I'm going to adjoin U to that. And then because U lives in the field there at the top, which is the square root of 2 and the 6th root of 6 adjoined to Q, we can literally make this tower, okay? So I can only make that tower if I know that Q of U lives up here. Remember, guys, Q is obviously contained in here. And if I assume that U is also contained in here, then this field contains Q and U. But Q adjoin U, by definition, is the smallest field that contains Q and U. So it must be inside of that one, right? So that's the idea. Okay, so we build this tower now, and the idea will be to think about the dimensions here. What is the dimension of the simple extension of Q of U over Q? See, I always like to go over Q because when I'm testing something over Q, I have lots of tests for irreducibility. I'm making a simple extension here, so I need to know what is the irreducible polynomial for U over Q, right? I would like to figure out what that is. Because whatever the degree of that polynomial is the dimension of this extension. So I'm looking for a polynomial that has U as a root and which has rational coefficients and which is irreducible over Q. Guys, I only have one polynomial on the board. And we are supposing that it does have U as a root. It clearly has rational coefficients. And is it irreducible over Q? Don't look at the coefficients. This is a 5th degree polynomial, so I can't just look at roots. This thing might factor as a quadratic times a cubic if I'm not careful. So I need to really make sure I know why this thing does not have any such factorization. And the answer is that this is irreducible by Eisenstein applied to the prime p equals 5. Remember Eisenstein's criterion. It just says you need a prime that divides every coefficient except the leading one, and such that the square of that prime does not divide the constant term. So in this case, we can use Eisenstein with p equals 5 and write down x to the 5th minus 10x cubed plus 200x minus 20, and that is my irreducible polynomial. And so that means that this dimension is in fact 5. Okay. Again, folks, I'm looking for a contradiction here. I'm doing this by way of contradiction. So the question is, what is the contradiction going to be? Right? Well, you see, I can also do my tower a little bit differently here, which is I could kind of start with Q and go this way and build another tower off on the side here. And I claim that, well, this number is going to be a 6. This is 6. Why is this 6? Well, again, I can look at the polynomial x to the 6th minus 6. That is irreducible over Q by Eisenstein. Again, we could apply P equals 2 or 3 to this, right? The constant term 6, the possible prime divisors would be 2 or 3. Either way, this is my irreducible polynomial for the 6 through 6 over Q. And so that's a dimension of 6. And then from there, I just have to get from here to the top. This is also a simple extension where I've adjoined the square root of 2. So this is either, okay, I don't maybe know for sure, but for sure the square root of 2 satisfies x squared minus 2. Now, whether that's the irreducible polynomial for the square root of 2 over this field, I don't know. It's not clear. But if this thing is not irreducible, it would mean that the square root of 2 is already in this field, and so this would then be a 1. Either way, what is this dimension here? It's either 6 or 12. Let's just play really dumb on this. Let's imagine we don't know whether this is a 1 or a 2. That's fine. This is either 6 by the Tower theorem, or it's 12, right? In other words, this one here, right, is 6 or 12. But take a look, guys. We already know that 5 divides it. So 5 divides 6 or 5 divides 12. Either way, we have a contradiction. This is impossible, yeah? That is impossible. We have a contradiction right there. And so we're done. What we're really asking here on this top branch that I didn't really fully explain is we're really asking, is the square root of 2 an element of Q adjoin the 6th root of 6? That's really the question. And that's maybe not totally obvious. So I don't really know for sure whether that's a yes or a no. So we don't have to know. If it does belong to the intermediate field, then this dimension is 1. Otherwise, the dimension cannot be more than 2. Because the element you've adjoined already does satisfy this polynomial. So you're not going to do any worse than 2 on the dimension there. Okay. Hopefully it makes sense. Ask me questions, write down any notes that you need to clarify with me as we go along, and catch up with me to ask about it if you need to. Okay, guys, well, I don't have a whole lot left up here on my list. Again, in the first review session, I did most of the group theory problems. I want to do a couple of things that are not about field extension theory, though, to kind of wrap up this review. So I'm going to start with problem 7, which involves a couple of true-false items. I generally don't like true-false questions for my exams because people just end up second-guessing themselves, and it's almost a psychologically challenging thing to think about. I would probably tell you whether this is true or not, and then just ask you to either prove it or give a counterexample. But it's a natural thing to ponder here, right? So if I take 2 maximal ideals and I perform their intersection, the question is, would that still be maximal? So we kind of have to put on our ring theory, ideal theory thinking caps now, since we've been doing something else for so long. But remember that there's lots of good examples of maximal ideals, and we're talking about rings. And so you have to think about what kind of rings could you explore for this if we're not sure. One thing that does make me nervous, though, one thing that does make me believe this might be false is that when I intersect 2 ideals, the result just gets smaller. It just gets smaller, right? So, you know, if I have my ring here like this, and then I had a maximal ideal, say M1, and then I have another maximal ideal here, which is M2, that's great, but look at the intersection. The intersection here, right? It sure looks like it's not going to be maximal, because it's kind of like, well, it's contained in, you know, either of the 2 original ideals that I started with. And remember, a maximal ideal is one where you should not be able to do this. You should not be able to take your ideal and then sandwich something larger than it in between your ideal and the whole ring. And it looks like that's what's going to happen right here. So my intuition is that this is false. And if you wrote this down, it's not really a counterexample, but it's certainly the right intuition for why it's false. And this would not be, I would definitely give you partial credit for even just kind of drawing a picture here with no real explanation to it. Obviously, however, once something is false, the best thing we can possibly do is give a counterexample. And when I'm thinking about rings, the easiest example of a ring that I can think of would probably be the ring of integers. This is a good choice. You can also use a polynomial ring, like f of x is a good one. If you're looking for something that's a ring but not a field. Remember, guys, that for fields, ideals are not very interesting, right? The only ideals in a field are just 0 and the whole entire field. So for something like an ideal theory question, fields are not going to be so good. So maybe something like Z would work. And we could think about some maximal ideals. A maximal ideal is one where when you mod out by it, you get a field. That's theorem 6.15. So I want to pick a pretty big maximal ideal, and Z, they're all principal. Every ideal in Z is a principal ideal. So let's take the ideal generated by 2, which is literally just all of the even numbers. So this would literally just be 2Z, right? And so this is maximal. If I want, I can just remind everybody here that Z modded out by the principal ideal generated by 2 is actually isomorphic to Z2. This could be proven using the first isomorphism theorem for rings. That's probably how I would do it. I would just create a function that takes an integer and spits out whether it's even or odd, a 0 or a 1 here, right? So 0 for anything even, 1 for anything odd. In other words, just reduce mod 2. The kernel will be exactly the even numbers. So, and it will be a homomorphism and it'll be surjective. So you can prove things like this. This is a very easy one, just using the first isomorphism theorem for rings. Anyway, Z2 is a field. ZP is a field, right, for any prime P. And because that's a field, then the ideal was maximal. And then I'm just going to say similarly, just have to pick another one, guys. It doesn't matter what you choose. We can pick the maximal ideal generated by 3. Okay, which would just be all of the multiples of 3. And this one is also maximal by the same exact reasoning. But if I now intersect them, if I take the principal ideal generated by 2 and I intersect it with the principal ideal generated by 3, now what I'm doing is I'm taking all multiples of 2 that are also multiples of 3, and I'm intersecting them. And I get actually the multiples of 6. I get the multiples of 6, right? That's the principal ideal. We know it has to be principal. And the generator for it is 6, as it turns out. And this one is not maximal. Again, I would want everything to be explained. Why is it not maximal? You can give 2 reasons. One would be if you take Z and you mod out by the principal ideal generated by 6, you get Z6, which is not a field. So you could point out that you don't have a field there. Or if you don't like that reasoning, you can also do the direct definition approach, where you literally sandwich an ideal, either the principal ideal generated by 2 or by 3, in between the ideal generated by 6 and the whole ring of integers. So either of those justifications would be fine, but that's an example that shows that this is false. So yeah, I always like to think of the integers for counterexamples if possible, but you can't always use the integers, of course. Sometimes we might have to do something else. Let's take another example of this type. Let's do part B of the same exact problem. So it's still true, false. Okay, but for part B, it just says if M1 is, let me just abbreviate the notation here, guys. It's all written out in the handout, but I'm just going to use the ideal notation, which is sort of the same as normal subgroup, and I'm just going to write the word maximal above that. So if M1 is a maximal ideal of R1 and M2 is a maximal ideal in R2, then is it true or false that if I take the Cartesian product, M1 cross M2, will that be maximal in R1 cross R2. This is true or false again. But we've certainly played a lot with maximal ideals. Feel free to pause the video here. I'm going to start talking in just a second. So if you want to think about it for yourself first, go right ahead and then I'll tell you what I'm thinking. I like to remember that theorem 6.15, right? Namely that if we have a maximal ideal, then the quotient R1 mod M1 would have to be a field. This is literally equivalent to the assumption that M1 is a maximal ideal of R1. And R2 mod M2 would also be a field. These would be equivalent ways of stating the assumptions. And then the question would be, so I'm just kind of scribbling for the moment because I'm trying to figure out whether this is true or not, but I'm just going to scribble down what this quotient would look like. If I took R1 cross R2 and I mod it out by this M1 cross M2, the question would be, is this still a field? Now, this may look a little bit familiar, and that's because there is an isomorphism here. And this can also be proven using the first isomorphism theorem for rings, because what we can do is we can break this up as R1 mod M1 cross R2 mod M2. And so now I would like to ask you, is it true that the cross product of two fields is still a field? That was actually in your homework, and it turns out it's not true. It's actually not true. This is in fact, this is almost never a field. The only way this could be a field, this kind of thing could be a field, is if one of the factors was literally the zero ring, right? Because you have zero divisors here, right? You actually have zero divisors because you could have like 1, 0 and multiplying it by 0, 1. Anytime you cross two rings together, you will never get a field, because this equation that I'm writing down here is never going to be acceptable. You have zero divisors, right? So in fact, the cross product is not even an integral domain. It's not even an integral domain. So what we could do here, if we wanted, guys, we could again just give a counterexample. This is also false, right? So I could take, let's just use the ring of integers in both slots. I could take the ideal generated by 2, which is maximal in Z, and I could take the ideal generated by 3, which is maximal in Z, right? But then when I cross them, this is not maximal. I'll put a slash through that. It is an ideal, but it's not maybe I have to put the slash through the word maximal. It is an ideal of Z cross Z, but it's not maximal anymore. It's not maximal. And again, why not? If we wanted to justify that, I could just take Z cross Z. I could mod out by the principal ideal generated by 2, cross the principal ideal generated by 3, and I can use that isomorphism that I was talking about a minute ago to write this as Z2 cross Z3, which is not a field. In fact, this is isomorphic to Z6, and Z6 is not a field. Or if you don't want to even do that, if you just want to leave it in terms of Z2 cross Z3, then you can just write down some zero divisors here, right? And again, anything that's a zero divisor, such as 0, 1 and 1, 0, anything that's a zero divisor is not going to be a unit. And if you have non-units in your ring, then you don't have a field. Great, so that's more than one example, of course, is possible, but that's kind of the way I like to look at that.
It's just like making it pretty.
Okay, guys, I know in the first review session, I did a lot of the group theory problems, but there was one off of the review sheet that I didn't do in the first review, so I'm just gonna do it now. We're almost done here. I would like to remind you how this argument works to prove that groups of certain sizes have to be abelian. And so this is a good one to work with. Let's suppose G has 207 elements in it. One of the first things you'll want to do, of course, is factor that. There's clearly a factor of 3 going into there, and I think that's times 69, which means I can go a little further with that and break it down as 3 times 3 times 23. So I'll try to give you numbers that are easy to factor, or else I'll just give you the factorization. But the way that you want to work this argument is you would like to create a subgroup of size 9 and another subgroup of size 23. Now, we know that those exist by the CELO theorems. So there's CELO 3 subgroups and there's CELO 23 subgroups, right, in this case. And there's always at least one. The first CELO theorem says there has to be at least one. Let's just figure out like how many CELO 3 subgroups do we have? Remember that this is a number of the form 1 plus 3k, and it has to divide the part of 207 that doesn't involve the powers of 3. So that would be 23. And so you can see from that, well, if a number is going to divide 23, it either has to be 1 or 23, but 23 does not have the form 1 plus 3k. So for that reason, n sub 3 is actually equal to 1. And so that means that there is a CELO 3 subgroup. I'll denote it as P sub 3. And since there's only one of them, it is a normal subgroup of G. And also the size of that CELO 3 subgroup, remember that by definition is the largest power of the prime that divides into the size of the group. So 3 squared is the largest power of 3 that we have in the factorization of the size of the group. And that means that P3 has size 9. Guys, any group of size 9 is always abelian. It is size P squared, right? Any group of size P squared is always abelian. So let's just note that as well. I'm going to note that P3 is abelian. Okay, remember, we're trying to prove that G itself is abelian. So it's nice to know that at least P3 is already abelian. Okay, let's look at the other CELO subgroup, the one that corresponds to the prime 23. In fact, it's usually a good idea to do larger primes first. Not always, but most of the time, when you work with the larger prime factors first, it just goes more smoothly. And you can see here's a good example of that, because a number of the form 1 plus 23L could never divide 9 unless it was equal to 1. So we're going to immediately get that n sub 23 is also 1. And so we have a CELO 23 subgroup. Since there's only one of them, that is also normal in G. And this time the size of that one is 23, which is the largest power of 23 that we have in this group. And anything that is of size of a prime is actually cyclic. So P23 is actually cyclic. And if it's cyclic, then of course it's also abelian. Any cyclic group is abelian. And so P23 is cyclic and therefore also abelian. So we're doing pretty well. We're doing pretty well here. We have a CELO 3 subgroup of size 9, which is abelian, and we have a CELO 23 subgroup of size 23, which is also abelian. The next step in this process, again, we've done this before. I'm just rehashing the argument again. There's no surprises here. What we need to do now is we need to form the product of those two subgroups. So we literally form P3 times P23, right? Because both of these subgroups is normal, this becomes another subgroup of G. Actually, it's better than that though. It turns out, I'm going to try to convince you just using Lagrange's theorem that this product is actually equal to G. Okay, why is that? Well, if we look at the Lagrange's theorem, note that P3 is a subgroup of P23, P3 times P23. And also P23 is a subgroup of the same thing. So if I put all of that together, right, guys, if I put all of that together and I use Lagrange's theorem that just says the size of a subgroup has to divide the size of the group, then we see that the size of P3 times P23 is a multiple of both 9 and 23. So 9 divides the size of P3 times P23, and 23 divides the size of P3 times P23. Right. So this size, the size of P3 times P23, it is a multiple of both 9 and 23. But the smallest multiple of both 9 and 23 is the entire group, which is 207. Right? So actually, and it can't be any bigger than 207 because that's the whole big group. So this is actually of size 207, which is the whole size of G. Actually, the whole size of G. So this isn't just a subgroup of G. It actually is equal to the full group G. So let's write that down up here. So G is equal to P3 times P23. And we are getting very close now to proving that G is abelian. Because after all, P3 is abelian, P23 is abelian. I just have to kind of figure out how to show that elements will cross commute. And for that, I'm just going to make one more note here. There's one more piece to the argument. What is the intersection of these two subgroups? This is another subgroup again. Remember, when you form the intersection of two subgroups, you get another subgroup. But this time we have a subgroup. This thing is a subgroup of P3, which means its size divides 9. And it's a subgroup of P23, which means that its size divides 23. So what number is both divisible by 9 and divisible by 23? The answer is it has to be 1. This has to be equal to E. This is just by Lagrange's theorem. Again, the intersection of the two subgroups is equal to E. Now, you might remember there was a homework problem, and I know it feels like an eternity ago, but there was a homework problem that proved that if two subgroups intersect trivially, and if both of them are normal in the original group G, then by a homework problem, and I wish I remembered which number it was, 8.221. Okay, I didn't remember which section it was. Okay, so we're thinking, I think those of us that are here on the fly believe that it is that one. I'm going to check right now, actually, just to be sure. Yeah, you don't need to do it. I've got it here. Yeah, so this is 8.2 number 21. What we know, guys, is that if you take A out of P3 and you take B out of P21, well, then AB is equal to BA. So that was a much earlier homework problem, but we're going to need it right now. In order to apply that homework problem, both subgroups have to be normal in G, and they have to have an intersection, which is E. Okay, so with that in mind now, let's prove that G is abelian. The last part of the proof now is to just put everything together. So proof that G is abelian. So I just have to take two things in G. So let's let, I don't know, X, Y be in, sorry, so let's take X and Y in G. And I'm going to write X as A times B, where A lives in P3 and B lives in P23. And I'm gonna write y as CD, where C lives in P3 and D lives in P23. And I'm just gonna look at x times y. So this is the last thing, x times y would be, well, obviously it's just A, B, C, D. Just write it all down. And I just need to get things commuted around a little bit. So I know that since A lives in P3 and B lives in P23, by that homework problem, I can switch the A and the B around. And by exactly the same reasoning, I can switch the C and the D around. I can rewrite those in the opposite order like so. And I'm trying to get the, what do I ultimately want to get down here? I ultimately want to get y times x, which means I ultimately want to get C times D times A times B. So actually, I don't think I did this terribly well. Let me go back here. I don't want to move the C to the far right. I want to move it to the left. So actually, let's take the B and the C, which are in the center here. The B lives in P23 and the C lives in P3. Well, those can be cross commuted, right? So I'm going to cross commute those and write them as A, C, B, D. And then the B and the D both live in P23. Remember that that's abelian. And also the A and the C both live in P3, which is also abelian. So I can switch the A and the C, and I can switch the D and the B. Am I getting anywhere close? Ah, yes. Now the A and the D can be cross-commuted by that homework problem in the middle here, and then I get what I want. Okay, so that finishes the proof. Sorry about that. Took me a little alphabet soup scrambling of letters here to get that to work out right. But that's how that argument works, and I hope that it makes sense. So practice a few more of those on your own. That's number 5 from the review sheet. And guys, I have done almost everything. I realize I left out number 21, but you know what I'm going to do? I'm going to let you read that one on your own. There's a typed up solution. It's all very well done. It's very similar to several of the other ones we did today. So I don't think I'm actually going to do it in this video. We've done a lot of problems this morning. Thank you for coming. Thank you for watching. And if you have questions about any of this stuff, I hope that you will let me know. Thanks. I'll see you again soon. Bye for now.